Hello everyone, let's have a look at another power example, okay, that is on your screens. So the engine of a 300 kilogram dragster exerts an average forward force of 53,000 newtons over the first 20 meters of its race. If the dragster takes 0.8 seconds to cover the first 20 meters, calculate the power developed by the engine. Alright, so first things first, everybody. Let's just write down what we know about this question. Alright, so we have a force which is equal to 53,000 newtons. Wow, that's a big force. Okay, and then we have a delta x, which is 20 meters. We also have a time which is equal to 0.8 seconds. They told us the mass of the dragster, which no one really cares about. Thank you very much for telling us, though. We appreciate it. And I think we need to calculate the power. All right, let's have a look there. Calculate the power developed by I was going to say Asian, by the engine. Okay, so we need to know what's the power of this engine power. All right, well, we know the formula for power for this example. Okay. Alright, we know that P is equal to W over T, which we also know equals to force, okay, multiplied by delta X over T, which equals to F times V. Alright, so what do we have here in this equation? We have a delta X, we have a T, and we have an F. We have all three, alright, of this equation, so we're going to use the middle one. Okay, so therefore P is equal to 53,000 multiplied by 20 over 0.8. Alright, therefore P equals to, and I'm doing this live on my calculator right now, 53,000 times 20 over 0.8 gives us a huge force, okay, or a huge power, sorry, of 1325000, okay, which is 13,025,000 watts. Okay, we can convert this though. We can divide it by 1,000 to make the answer just a little smaller. Okay, we can say which therefore equals to 1,325 kilowatts. Okay, we can do that. We can make that kilowatts instead of saying 30,025,000 watts, which is quite a lot of watts. Okay, we can just do that. You don't have to do that. You can leave it in watts. I made it kilowatts just to make the number a little more easier to read. Okay, but that is the answer for that example. Okay, so that was probably the most straightforward example out of the three we did. Okay, so what we're going to do now is we're going to continue with this example train that we're on, but first we're going to have a look at how to calculate the power of an electric motor. So let's consider an electric pump used to pump water out of a borehole. Okay, we know this very well. We know all of us should be very familiar with a borehole, all right, and a water pump. I actually have one at home, by the way, to water my garden, my back garden. I actually have one at home. Okay, so we can actually calculate the power of this, believe it or not. So the pump will pull water through a vertical height h at a certain rate, and this is usually given in liters per minute, all right, which is L per min to the -1. All right, I'll write that a little clearer on the screens over here. Let's just get a clear page. Here we go. So usually given in, first let me draw my margin for our example. It's usually given in liters per minute. Okay, sometimes calculated, sometimes in liters per second. Okay, but usually in liters per minute most likely. Okay. Right, so our example, let's just clear it up. Our example All right, let's calculate the minimum power required of an electric motor pump to pump water at a rate of 120 liters per minute from a depth of 12 meters. Okay, so they've given me we need to calculate, first of all, what we're going to need in order to calculate this question is we need the mass of water. Okay, we need the mass of water. One thing we need to note over here, that the force at which it pumps, all right, is non-conservative. There's a non-conservative force, okay, when the pump pulls water up. Okay, it's non-conservative. We also need to know that it pumps the water up at a constant speed. All right. So therefore, the change in EK, or the kinetic energy of the water, is equal to 0 because it's a constant speed. There's no change. And then, of course, that 1 kilogram or 1 liter of water, 1 liter of water is equal to 1 kilogram of water. All right, so we need to calculate the mass of water. So the mass of water needs to be calculated in this question. Okay, we need that. Okay, and the question asks us specifically to calculate the minimum power, okay, required. Okay, so we also need to calculate the power required. Okay, so how are we going to approach this example? Okay, how are we going to approach this example? Well, first things first, we need to do is need to calculate the work. All right, so the formula, work of a non-conservative force is equal to the change in EK plus the change in EP, which is potential energy. We know that this is equaling to 0, so that cancels out. So therefore, the work of the non-conservative force is going to equal the change in EP. All right, which is equal to mg hf minus hi. Okay, I took h out as the common factor, okay? Then we know that if it's pumped up, all right, we know that its initial height was 0. All right, so therefore, the work of the non-conservative force of the pump that the pump is doing is going to equal to mg hf. All right. All right, something that they didn't put in here that I forgot to put in there, that h is equal to 12 meters. Okay, h is equal to 12 meters, so therefore this is going to equal to the mass of water, which we first need to calculate. So let's calculate the mass of water here at the bottom. All right, so they told us that the mass of water over here was 120 liters per minute. So 120 liters per minute is equal to 1 liter is equal to 1 kilogram. So times 1 kilogram over 1 liter, which is equal to 120 kilograms. Okay, so therefore the mass of water is 120 kilograms multiplied by 9,8, which is gravity, multiplied by 12. Therefore, the work of the non-conservative force is equal to, let me put NC there, is equal to, I'm doing this live on my calculator again, all right, 14,112. 14,112 joules. All right. So now we can go ahead and we can calculate the power. All right. So power is equal to W over T. Now they gave us the rate at which it pumps water is 120 liters per minute. And we know that time is measured in seconds. So time is measured in seconds, while work is measured in joules. We have our joules already. All right, so therefore P is equal to 14,112 joules all over, now watch this, 60 seconds. All right, because it pumps 120 liters per minute. So not per second, but per minute. 120 liters per minute. Okay, so therefore it has to be 60 seconds. All right, And if we punch that into our calculator, we'd get the minimum power needed to pump water from the borehole is 235.2 watts. Alright? 14,112 joules divided by 60 gives us an answer 235.2 watts, which is the minimum power required to pump water at a rate of 120 liters per minute from a depth of 12 meters. Okay, and that seems just about right.